Okay, so hello everyone and welcome. In this video, I'm going to talk about the new challenge that we have on Kaggle, multilingual toxic comment classification. And there have been many challenges like this in the past called toxic comment classification, but we never had multilingual. And yeah, thanks for the hat. I couldn't find mine. So in this video, we are going to see how we can use BERT and apply it in this competition data, and also how to do the same using TPUs. So if you have seen this competition, if not, it's okay because I'm going to go through the data a little bit. So let's look at the data. So here we do have a lot of files and we have toxic comment train, unintended bias train. So these are from first competition and the second competition of toxic classification. And then we have a test.csv for test data, and we also have a validation data, validation.csv. So these are the major files that you need. And then you also have some processed sequences of sequence length 128, but you probably don't need that. You probably want to use larger sequences. So what do we have here? We have ID, a comment text, a language, and whether it's toxic or not. So let's look at the data a little bit first. Okay, probably this one. So we have the comment text, and we have the toxic column, whether it's toxic or not toxic, and that's all we need. And we also have this other data set, probably this one. Okay, so here we have the toxic column too, but here you see the toxic column is real values, floats. They can be between 0 and 1 or 0 and 1. So, and we have the test data set. So test data set is some content text and then the language. So to start with this model, if you have seen my previous video on BERT sentiment, it's going to be quite useful and quite fast. If not, it's okay. So when we made the BERT sentiment model using the IMDb dataset, we created a small kind of framework that we can train on any similar dataset. So what we are going to do is we are going to use that framework. So in that we had dataset.py. So what I'm going to do is I'm just going to copy this thing from here and start building our model. So let's say I create a new folder called source, and inside that I have dataset.py. Now it will be very useful if you code along, because then you learn more. So what I'm going to do here is I'm just going to modify this dataset class for our new data. So in our new data, we do have a review column. Let's say it's called comment text. So we have review. So everywhere where we have review, I'm just going to replace it with comment text. And we do have a target column, so that's fine. Now we don't need to change anything else in this BERT dataset class. So here you have inputs. So I'm using encode plus from Hugging Face tokenizers that encodes your first string and the second string. but here in this case we don't have any second string, so we're just going to use none, and we specify a max length and the special tokens for BERT. And then using the max length, we calculate the padding length, which is max length minus the length of IDs, and then we pad on the right side. So for BERT, you pad on the right side, and then we return IDs, mask, token type IDs, and targets. Okay, so far so good. Now we will look at the model file. So we can either look at engine or model. Let's look at the model first. So here we have created a BERT based uncased model. So again, just going to use that one because we have already done it. And here I'm taking the BERT model from transformers, the pre-trained model, and specifying it in config BERT path. And then I'm using a dropout, and I have a linear layer. So a lot of people in my previous video commented saying that why do we use this output? Why don't we use the other one? So we can also try using the other output, but this is flat. So for every sample you have a vector of size 768. So we can just use it directly, or we can also change it. So we can probably change it for this video. So now we don't need the second output, and I will say that we can use the first one. So what we can do is we can write here, we can do some kind of mean pooling on the first output. So this will be torch.mean, and output was 01 and 1. And similarly we can also do max pooling. So in max pooling, here I've used underscore because the second value is indices. We don't need the indices, and everything else remains the same. Now we can concatenate it. So both of these will be vectors of size 768. So my concatenation will be cat equal to torch.cat, and inside that we can have average pooling or mean pooling, max pooling. Okay, access 1. So we got this one, and now we change this to cat. So we added the dropout, we have an output layer which is linear, and now one more thing that you want to change is multiply it by 2, because now you have mean pooling and max pooling. Okay, so this will be our model that we can use. Now if we go back to our BERT sentiment model, we can go to engine.py, which we had written before, and it was written for binary classification problem. So I'm just going to take everything from here and create engine.py. So what do we have here? So we have a training function that takes the data loader, takes the model itself, optimizer, device, CUDA, GPU, CUDA, CPU, and scheduler. And then you put the model in train mode, go through all the batches inside a data loader, and then you have IDs, the token type IDs, the mask, and targets. And then you put them to the device that you're using. So everything looks fine here. We have targets, which is float, even now it's float, and then you zero grad the optimizer, you pass everything through the model, calculate the loss, do backpropagation, and step the optimizer and scheduler if you have scheduler. And similarly you have the eval function. So this is important because if you don't have a lot of GPU memory, so you want to use with torch.nograd and then do the same thing without the loss stuff that you did in train. So it's just a copy paste. Okay. The BERT sentiment is available here. I have posted the link in the chat. So I guess that works. So we are almost there. So now we just need to write our training loop, and that will be all. So we go to we have dataset, we have engine, we have model. Yeah, one more important thing was the config. So config specifies everything that you need in order to run. And here we go. Here we'll do config.py. So we can we can specify for our project. So we are importing transformers. We have a max len of 512. We can specify some kind of batch size and validation batch size, and then path to the BERT model, and where you want to save the model, that's the model path, and training file. So in this case, I'm just removing the training file from here. Okay, and now we can start writing the training script itself. So which is also quite simple and similar to what was already done. So we have train.py, and I'm just going to take everything from here. Okay. So here we have all the imports, and now you want to change the arguments in dataset. You want to change the data itself. So let's try doing that. So we have two different CSV files. So I'll say df1 is pd.read CSV, and this file is called Jigsaw Multilingual toxic train toxic comment train.csv. And another one that we have is I'll have to check, toxic comment train unintended bias train.csv. And from both of these, we just want to use only two columns. So I can just do use calls, comment text, and toxic. And I can do the same for the other file. Okay, and this will be your df2. Then you have the full df train will be pd.concat. So I'm just joining these two data frames, df1, df2. And I will also reset index and drop it. So we got the df train, and now we want df underscore valid. Df underscore valid will be pd dot csv. I think just validation.csv. Okay, so we have the training data frame, we have the validation data frame. So we don't need to split it anymore. We don't need to reset the index. And here, instead of review, we have comment text in BERT dataset. So comment text, review, comment text, and target, instead of sentiment, it's toxic dot values. So instead of sentiment, we have toxic. Okay. So what have you done? What have we done till now? So we have these two data frames. We combine them, create a big data frame. We have the validation data frame. So this validation set is provided from Kaggle, and then we have then we call the dataset object class, and we create train dataset. We create the train data loader using a batch size which is defined in config, and then we have a valid dataset and a valid data loader. So everything here till now it's the same, and even after that everything is same. So the difference between df1 and df2 is there are two different CSVs which are provided in the competition. So both have a bunch of sentences, and both are different from each other. So now we create the model, the BERT base and case model that we modified a little bit just now, and then we do the same thing. Then we don't change anything at all compared to the sentiment model that we had created. So we keep everything the same because it's a benchmark. So it's now up to you. So you need to change optimizer parameters a little bit and play around with it, experiment a little bit to improve the score further. So now I have 2 GPUs, so I put everything in. So I change model to data parallel model, and then I just call engine.train function with all the arguments, and then I say if the outputs is np.array of outputs greater than 0.5, and now instead of accuracy we have to calculate AUC score, which is also quite easy. So ROC AUC score. So now I will say, okay, if ROC AUC score, I can just keep the same name, accuracy, but in this case it's ROC AUC score instead. If it's greater than best accuracy, then we save the model. And I think that's all. Then you're done with building the first model. So now we can try to run it, but I don't have the data, so I'll just quickly download the data. So you create an input file. No, I don't have to delete the line. Yes, I do have to delete the line. So good point from Firas. It should be targets. So a very interesting thing here is targets are values between 0 and 1. So for one of the data frames, it's just binary, zeros and ones, but for the other one, it's not. So now it's up to you. What do you want to decide? How do you want to train? You can train on everything. You can say like everything greater than equal to 0.5 is my is 1, or you can just train on all the float values. And What I've seen till now is floating is training on the float values is much better than binarizing them. But yeah, it's something that you should try. So my targets will be greater than equal to 0.5. Which threshold? Okay. So I've been just copying the data. So now I have created a input folder with all the CSV files in it. And now we can start training the model. But I don't have BERT based on case. One more thing about this competition that says in the name itself, it's a multilingual, BERT multilingual. So we need to uh, use the multilingual model, because you can use BERT based on case, but it's trained only on English data, and then it's not going to perform very well. So you will get some score, but it's not going to be very good. So it's better if you use the multilingual model. So what I can do here is I can just change the model to multilingual, and this has also been shared in the competition forums now. So you can use it from there, and now we can try to start training the model. So I'm just going to reduce the batch size to max length to 256, and then see if it works. So yeah, okay, so it didn't find some file. Okay, so let me see. Jigsaw multilingual. Okay, the file name is incorrect, so I'm just gonna fix that. And let's try training it again. And if everything is fine, it should work. It's not much of change because you have already created the framework. Okay, so yeah, I should import torch. So missing import. Let's try again. So the issue with line 71 was I was thresholding outputs instead of targets. So we have to threshold the targets instead, because targets are values between 0 and 1. Okay, so this seems to be training now. You can see like this is going to take quite a long time, it seems. I'm using two 2080 Ti's, so yeah, it's taking a lot of time even on those. So always a better way would be to just cancel it and try to train it on TPUs instead, and that's what this competition is meant for. So now we can go to Kaggle, back to Kaggle, and create a new notebook. So go to the new notebook, and I will select one with TPU, but I'm not going to select it right now. I'm going to select it after we write the code. Or okay, let's do that. Let's just select it right now. So we create the notebook. Okay. So now we need to wait. So you can see now I have the TPU accelerator, and using TPUs it's going to be super fast, and we will see now. And we have already done all the work by creating a simple model first, so we can just copy paste stuff from there. We don't have to write a lot of code again. So most important things that we need, we probably need OS, or maybe not, I don't know, but let's just keep it and let's delete everything else. And we need import torch.nn as nn. Hey, let's see what else we need. So for dataset we need import torch. Okay, so I get it from there. And okay, and from model we have torch, we have torch.nn, we have there is transformers now in kaggle, so we can use that. For engine, do we need anything new? We don't know, just copy tqdm, probably need it. And we also need something from config. No, but we do need the config, so we'll come back to that later. We need scikit-learn. We need all these things here. Okay. Yeah, I think we have everything that we need for now. So let's start. So what I'm going to do is I'm just going to copy paste everything from the model we just created, and you see how simple it becomes when you have created all this boilerplate for some problems. You can just transfer it to another problem very quickly. So it's going to probably take 20 minutes once you have BERT sentiment made, 20 minutes to just copy everything from there and arrange it. So we need the BERT base uncased model that we have created. So I'm just going to put it here. And we also need dataset. So I'm just gonna copy it from here. And now we need everything from engine. So this also comes here. I would rather add it as a dataset or a script and then import them, but this is also fine. So now we have that, and now we can start writing the training for TPUs. So to write training for TPUs, we can just copy paste everything from here. And it's just small changes. Okay, so we have this run function. So we input the training files, everything remains the same. Now, when you use TPUs, you have to use the distributed sampler, which is going to distribute the data on different TPU cores. So you can write train sampler equals torch.utils.data.distributed sampler. And here you have train dataset, which is defined above, and you define how many replicas you have. And now you need to import a little bit more. So we go back up, and we import some. So for using TPUs using PyTorch, if you want to use TPUs using PyTorch, you have to use torch XLA library. So import torch underscore XLA, and we have to import torch XLA .core.xla underscore model as XM. So now what you can do is you can say how many replicas you have. Let's go back there. Okay, and this will be xm dot num replicas, sorry, xm dot xrt underscore world size. So if you have one TPU, you have 8 cores, so your world size is 8. And now you have here rank. So rank is just the ordinal of the core, so you can do xm dot ordinal, and you can do shuffle equal to true. So let's look at this one. Distributed sampler. And this is from Kite, but I think it should be fine. So number of processors and then rank of current process within number of replicas. So you zero between 0 to 8 and 0 to 7, and this is 8. So you got that, and now we have the train data loader. So we will change it a little bit. Num workers 4 is fine. Now my sampler here will be train underscore sampler, and there is a problem in when using TPUs. If you don't have equal batch sizes, it's going to crash for some reason using PyTorch XLA. So I'm just going to do drop last equal to true. And let's see, we don't have config anymore, so we just do train batch size. So we need to remove config from everywhere, and we do the same thing like we did here for validation dataset. So I can just call it valid underscore sampler, and valid dataset, and then you have the same things. Now you don't need to do drop last equal to true for valid. Everything else remains the same. Added it wrong position. So here. So you got the valid sampler and valid data loader. And now you have the device, which remains the same, model remains the same, BERT base uncased, and device should change obviously. So you have xm.xla underscore device. That's your XLA device, which is TPU in this case. Now you have the model, and you have these parameters. Let's wait for this one. And then we have the number of training steps. So now number of training steps will change a little bit. So we had length of df train divided by train batch size, which is fine. And now you divide it by the world size, xm.xrt underscore world underscore size, and this remains the same. So that's your new number of training steps. So in this case, I'm doing learning rate 3.3e minus 5. So I'll just say my learning rate is 3 minus 5, but that also needs to be multiplied now by the number of cores you have. So xm.xrt world size. You don't need this data parallel thingy anymore. And you have train function, outputs targets come from eval function, and you have this array, which is fine. And instead of saving the model using torch.save, you will be saving it now using xm.save instead. And that's going to save your model, and then you can just load it in a GPU or CPU to serve it. Everything else remains the same. So the num training steps gets divided by the number of cores you have. So that's what I did. I just added xmxrt world size. I think everything else looks good. We need to fix few more things. Let's see. We don't need this anymore. Everything here looks fine to me. And here everything is okay, I guess. Optimizer. So when you're using XLA, you have to do xm.optimizer underscore step, and inside that you have to do optimizer like this. And then you can do scheduler dot step, which is fine, and everything here looks okay to me. Yeah, one thing is, let's not use TQDM, otherwise it will start printing on all devices. So I just remove TQDM from here and TQDM from here. Now, if you want to track something, then you can probably add something like, okay, if batch index %10, if this is equal to 0, then xm.master underscore print. So this is going to print only once. So batch indexes is equal to batch index, and then you can also print loss is equal to loss. Okay, so do I need anything else? We have the loss function, we have the training function. Here everything is okay. are we training it in a correct way? We have the device, which is XLA device. Yeah, okay, so we also need a parallel loader for this one. Okay, so you need to import more stuff. So import torch underscore XLA dot distributed dot XLA underscore multi processing. So we are going to use multi-processing as XMP, and import torch underscore XLA dot distributed parallel loader. So do we need to use loss.item? Yes, probably. So let's fix that. Where was it? Do I need to use loss.item, or it can just be loss? I think it's fine. Looks fine. Okay, so now we need to change a little bit more. So for training function, you need to change the training data loader. You need to wrap it inside parallel loader. So I can say parallel loader will be pl dot, and here goes your train data loader and the device which you're on. And same thing you need to do for eval function. So we have the training function, and now this one will become, it's the data loader, it's just parallel data loader. So para underscore loader dot per device loader, and then device. So data loader for that device in simple ways. And you have a parallel loader for validation. So valid data loader, and then you need to take this from here and plug it in here. Okay, so I guess we are done. Okay, yeah, thanks for letting me know. So I guess we have everything that we need. Have we removed config from everywhere? So let's remove config from everywhere. No config. Eval function, no config. Optimizer. So yeah, we need to remove this one. And tokenizer and maxlen. So now we set a few values using the config file itself. So we go to config and just take all of these, put them here. Word path, now this has to change, so I need to add a new data set. let's add datasets. So we need the BERT based multilingual. Okay, sometimes this happens. Okay. In the last loop, I have config. Yeah, this one. So I believe we have everything. Now you need to wrap this function a little bit more. So I'll say def underscore multi processing function, and it takes 2 arguments, rank and flags. So this thing you have to look up, torch dot. So you set a default tensor type, set default tensor type, and this can be torch dot float tensor. So you need to do that, and then say okay, run function, run the run function, and torch XLA you need to spawn these different processes. So we can say okay, flags is, or yeah, okay, so let's say xmp dot spawn the same multiprocessing function, and it takes the arguments, flags, which is nothing, and procs, which is 8. So now you have 8 different cores of the CPU, and start method equal to fork. So now let me add one more dataset to it. BERT base uncased. So we add the data. Okay. So now we have added BERT base uncased and also multilingual uncased. We will be using BERT base uncased first, just to see what's happening. So this will become BERT base uncased, and to run this you need one more thing. So let's go to kaggle. So you need to install PyTorch XLA, Torch XLA, and there was a discussion from today, and yeah, we need to run these 2 commands. So you can just add it in top of your notebook. Okay, so now we have everything, but we need to change couple of paths. So this should since we had a data set, this path has changed. So I'll just change that one and this one. Okay, so now you can run this with BERT base uncased, and it's going to work. The only problem with the PyTorch XLA is it creates copies of data and copies of your model in multiprocessing mode. So when you're using BERT base uncased, it has a vocab of like 30,000 words, but BERT multilingual has a vocab of over 100,000 words. so you won't be able to run it, or I was not able to figure out a way to run it on 8 cores. And so what you can do is when you're moving to BERT Multilingual, just change this to 1. It's going to be slow, I know. It would have been 8 times faster if you did 8. But one more good thing about this is you can increase the batch size. So we had a batch size of 8 on 2 GPUs. You can use a batch size of 256 with a max length of 128. And yeah, you can also increase this to 64. So it's quite fast training. And I have already created a training kernel, so I'm not going to run this one. I'm just going to show you the other one. Okay, so we have these 2 lines first that we saw, and that installs XLA, everything needed for that, and then everything remains the same. So now here, okay, so this one I forgot to copy. You also need the average meter if you're using it. So we have the same model, BERT base uncased, and that's the multilingual. So we will be loading multilingual weights, and you have the data set. And after that, we have a run function. So the only thing different in this notebook and what I wrote just now is I have taken the training loop, the loss function, and the evaluation function inside the run function. So it's in the scope of only the run function, but it's not required. So you have the training loop and you have the evaluation loop. Just have to remember that it should be xm.optimizer step and inside that optimizer. So this is one change for TPU, the first one. The second change is you should have a distributed data sampler. Then the third one is the device itself, xm.xla device. Then learning rate, which is a very important change because you now have multiple cores, you're running on many different cores, so you have to take care of batch size, learning rates, and number of training steps. So these 3 things become very important. How can you change the number of training steps? Is by changing the number of epochs. Then you have to wrap the data loaders in parallel data loader, right? And here I'm using xm.masterprint. You can also use that. You don't need to export this. I'm just doing it. And then you have the spawn. So now you will see that after every batch, so it's going to tell me, okay, I have 3125 steps. It's going to tell me that because I have printed it here. And after every 10 batches of data, it's going to print me some loss value, just like we did. And the good thing about this model is, so now this notebook is using BERT Multilingual, and you see I'm using n-prox equal to 1 because I was not able to fit that huge model. But if you find a way to do that, then comment on the video, let me know. It would really be cool to make it even faster. And yeah, even after first epoch you get a AUC of 84. So I trained for 2 epochs, and I see like in the second one it drops to 0.839, 0.84. And then yeah, you have an exception, but that's from TPU. You can ignore that. Till this point we have saved the model, and that's all we need. Okay, so now you have the model saved, which will come in your output, model.bin. Okay, make these notebooks public. Okay, yeah, so the notebooks are public, and now you need to create a inference kernel. So inference kernel is also quite easy. You have everything, you have the model, so I'm just copying the model again. And when you save using xm.save, when you save the model, it saves you in a format which you can use on CPU or GPU, anything. And then you have the BERT dataset for test. Now a little bit modification here that I did was to remove target, because you don't have the target, right? And after that, I read the CSV file. You have the tokenizer from Multilingual, and BERT base uncased again. Put it to CUDA and load the model files itself. So this model.bin comes from the training kernel. This one, the training kernel. And now you can start making predictions. So for making predictions, you can just copy the eval function. So you don't need anything else. You have to remember, in this competition, in the test dataset, test.csv, it's called content instead of comment text. So that's the only difference. And I used a max len of 192. You can use anything that suits you. And then, yeah, this thing I always keep forgetting. So this is so that you don't go out of memory. Wrap it in this function, and then you make predictions on all of them. So one of the things, yeah, I didn't do inference on GPU, because if we have GPU, then I think it's fine. No specific reason. And then you can create predictions. Now the evaluation metric for this competition is AUC, so you can have any kind of real number that you want. And I'm also making this kernel public, so you can go and take a look and try to improve the score further. And if you find something that's not working, there's something wrong with something, let me know. This kernel currently should give you quite high score, I think, yeah, in top 10, but you have to also see that the competition has just begun. So there's a lot of cool things that you can do there. You can also use BERT base uncased, and with 8 different cores of TPUs. So to do that, a very simple thing would be to just translate the data sets. So you see, in this competition, you have a validation set and you have a test set, and everything, you have everything in your hands. So you can just do some kind of offline translation, translate everything to English, and use BERT base uncased. To improve more, you can also try to combine it with a multilingual model. So I think that's it for today, and I don't have anything else. If you find something wrong with my notebooks or the code itself, because I'm going to put this code on GitHub too, so you have the GPU code and the TPU code, both of them. If you find something wrong, then let me know, and let me know how I can improve further. And if you like my videos, don't forget to like and subscribe, and see you next time. Goodbye.